Let's step back and see what we've done here. For these various processes, we've established something about the work, whether it's in, out, or zero. We've established whether the internal energy change is positive, negative, or zero. With this preliminary analysis, we're in great shape then to simplify the first law specifically for that process. So let's do that for the constant pressure process. So we have the heat transfer on a net basis in minus the work out on a net basis, and we know that the work is out, so we can probably just write that as net out, knowing that will be a positive quantity. And we also see that the internal energy change is a positive quantity, so we include that here. And let's then just solve for the heat interaction. So we have then the net heat transfer in must equal then the net work out. I'll just write out because we know there is no work in, and that's going to be positive, and the internal energy change, which is also positive. So we conclude with the sum of these two positive terms that the left-hand side, that the heat must be in, so that Q net in is indeed greater than zero. It's a positive quantity, so that Q net in just equals Q in. We can now take a look at the constant temperature process and do the same thing. We have then that the net heat transfer in minus the net work out. And again, we've established we have work out, so let's just write work out there, equals the change in internal energy. And we have just deduced that this must be equal to zero. So when we solve for the heat interaction, we simply have that the net heat transfer in must equal the work out. And this we have already decided is the work out, a positive quantity. So the net heat transfer in is the heat transfer in. So once again, we have the net heat transfer in is greater than zero, positive quantity, and we're just left with the heat transfer in. Let's take a look at what we can do to compare the magnitudes of these. Which of these two processes, the constant pressure or constant temperature, has the larger heat transfer? So let's, for the constant pressure case, we can write our rearranged first law, that the heat transfer in was equal to the work out plus the change in internal energy. And let's then also write then for our constant temperature case that the heat transfer in was just equal to the work out. We had previously concluded that this work out, the work out at constant pressure, was greater than this work out, than the work done at constant temperature. And we see that we're adding to that a positive quantity. So clearly the sum of these two terms will be bigger than the work out associated with the constant temperature process. So we conclude clearly then that the heat transfer in for the constant pressure process must be greater, and maybe even substantially greater, than the heat transfer that we needed to supply to maintain constant temperature. So this analysis is very powerful to understand what's going on and comparing these processes. And also, if we were to just go back and look at this, this is an interesting circumstance in and of itself, in that we're supplying just the correct amount of heat to keep the temperature constant. If we were to supply less heat than the work being going out, the temperature would fall. And Likewise, if we were to have a greater amount of heat than needed to equal the workout, the temperature of the gas would increase. So once again, you see the power of the first law and the way that you can use it to analyze and understand what's going on.